Hey everyone, Mr. Houck here. In today's video, we're going to be looking at a couple of practice problems to help prepare us for the performance final in pre-calculus. Let's go ahead and get started. This semester, so far, we've gone through 3 units. We've had Unit 1A on trig functions in the unit circle, Unit 1B on graphing trig functions, and Unit 2 on vectors and complex numbers. Your performance final on Monday, November 16th, will consist of 1 problem from each of these units, and you'll have to complete 2 of them. I'm going to take you through 1 problem from each unit that you can expect to see on the performance final, and I'm going to show you how to answer them so that you can receive full points. Okay? So here for Unit 1A, trig functions in the unit circle. For each problem, we're going to need to set up and label a right triangle in the appropriate quadrant on the unit circle in order to solve for an indicated trig value. We're going to need to show all work, and we're going to need to write an explanation for our work. So, let me show you exactly, and I'm going to do example 1 here only for this section, but let me show you how you can get full credit if this were a problem on the performance final. So reading the instructions, we need to set up and label a right triangle in the appropriate quadrant on the unit circle. So, let's see if we can find this appropriate quadrant. Well, we're given that the cosine of theta equals -1/3, and the theta is between pi and 3 pi over 2. Well, let's think about this. If theta is between pi and 3 pi over 2, well, pi is 180 degrees, 3 pi over 2 is 270, and if we look at our unit circle, pi, 3 pi over 2, everything in the middle of those 2 values is quadrant 3. So we are in quadrant 3. And we need to set up and label a right triangle in that quadrant. Well, if you look at your unit circle reference guide, if you look at the bottom right, I have given you a little image as to what it should look like when you set up a right triangle for each quadrant. Quadrant 3, this is what our right triangle should look like, and our angle theta should be in this corner. So let's go ahead and set that up. I'm going to draw, here's my negative, let me get that a little better. There's my x-axis, here's my y-axis, and there's my right triangle. Again, I want the 90-degree angle right here, and I want the angle theta right there. Now, we're told that cosine is -1/3, but we also know that cosine is adjacent over hypotenuse. So, what that's telling us is that the adjacent is the 1, the hypotenuse is the 3. Now, the hypotenuse is always going to be positive. And remember that hypotenuse is across from the 90-degree angle, so this side right here will be 3, which means that this side will need to be the -1. Now notice it's negative because this leg of the triangle is running parallel to the negative x-axis because we're in the 3rd quadrant. Also, this is the negative side of the y-axis, so we know whatever answer we get for this leg of the triangle is also going to have to be negative. So let's go ahead and solve for that. Because we have a right triangle, we can use Pythagorean's theorem. So I'm going to say a squared, a being the missing leg that we're looking for, plus -1 squared, which is the leg we know, equals the hypotenuse squared, 3 squared. Well, -1 squared, that's going to be +1. 3 squared is 9. Subtracting the 1 from both sides, we get a squared equals 8. And if a squared equals 8, let's take the square root of both sides, and we get a equals 2 square root of 2. Now, notice this is going to need to be negative. Negative because we're in the 3rd quadrant. Negative since quadrant 3. So let's go ahead and put that leg in, -2 square root of 2. And now what we need to do is we need to solve for the cotangent of theta. That is the indicated trig value that we're trying to solve for, cotangent of theta. Okay, well let's think about what we know about the cotangent. Let's see. We know that the tangent is opposite over adjacent, and the cotangent is the reciprocal of tangent. So instead of being opposite over adjacent, the cotangent will be adjacent over opposite. Well, looking at our angle theta, the adjacent leg is -1. The opposite leg is -2 square root of 2. So this will be -1 over -2 root 2. The negatives will cancel. We also know that we don't like the square root of 2 in the bottom, so let's go ahead and multiply numerator and denominator by square root of 2. And this will get us square root of 2 over 4. We're getting the 4 because square root of 2 times itself, square root of 2, will give us a 2, and then you multiply that times the 2 here, and we get a positive 4. And once again, this is positive because the negatives cancel each other out. So this is the solution to this problem. And let's make sure that we've answered all the parts. Did we set up and label a right triangle in the appropriate quadrant on the unit circle? Yes, we did, and we labeled it correctly. Did we solve for the indicated trig value? Yes, we did. Did we show our work? Yes, we did. Did we write an explanation for our work yet? No, we have not. So let's go ahead and write our explanation. So our explanation doesn't need to be anything complicated, but let's just write down exactly what we did. We set up a right triangle in quadrant 3 since theta is between pi and 3 pi over 2. Then we used cosine of theta equals negative 1/3 to label the triangle. Next, we use Pythagorean's theorem to solve for the missing leg. And finally, we used our triangle to solve for cotangent of theta. Okay, and that's an explanation that I would accept because that explains everything we did in the order that we did it. We set up a right triangle in quadrant 3 since we know that theta is between pi and 3 pi over 2. We use the cosine of theta equals negative 1/3 to label the triangle. We use Pythagorean's theorem to solve for the missing leg. And then finally, we use the triangle to find the cotangent of theta. That's an explanation of our work, and that would be perfectly fine. If this was a problem on the performance final, this would get full points, okay? Again, because we met all conditions in the problem. Let's now go and look at a problem from the second section, Unit 1B, graphing trig functions. And for this one, I'm going to go ahead and use, let's look at the second one. We did the first problem in the first section. Let's do the second problem in the second section. So we have y equals 1/2 cosecant of x minus 1. Let's read our directions. We want to graph at least one period for each trig function on the blank graphs provided. If the function has an asymptote, then it must be graphed. Make sure that key points on the graph are plotted clearly. I cannot stress this enough. Key points need to be plotted clearly. Asymptotes need to be graphed as well. I need to be able to see exactly what you're graphing, and the graph needs to be easy to read. So we have y equals 1/2 cosecant of x minus 1. Let's take a look at exactly what we want to do here. Well, since we have y equals 1/2 cosecant of x minus 1, if we think about it, when we talked about graphing secant and cosecant, we talked about graphing them using their reciprocal functions. And what is the reciprocal of the cosecant of x? When we think about the reciprocal for the cosecant of x, that's going to be the sine of x. So what I want to do is I want to turn these transformations, I want to map them onto sine instead. So I want to graph y equals 1/2 sine of x minus 1. And the way that I'm going to do this is I'm going to graph the parent function of sine, apply the transformations, and then use that transformed function of sine to graph this transformed function of cosecant of x. So let's look at the parent function of sine first. All right, so when we think about the key pieces to sine, we have 0, we have pi over 2, we have pi, 3 pi over 2, and 2 pi. These are the key points that we normally look at with sine. And we know from the parent function of sine, the sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi is 0, the sine of 3 pi over 2 is negative 1, and the sine of 2 pi also 0. Now let's look at the transformations here. We have a 1/2 being multiplied on the outside, and we have a -1 being subtracted on the outside. The -1 represents a vertical shift, and we know that vertical shifts affect the y values. So for the y values, we're going to need to subtract 1. We know that multiplying by 1/2 also affects the y values. It either stretches them or shrinks the y values. So we're also going to need to multiply the y values times 1/2. Now, we're going to follow order of operations. We're going to multiply times 1/2 first, then we're going to subtract 1. But notice that none of these are affecting the x values. So there are no changes here in the x values. So just to make our points stand out a little clearer, these transformed points I'm going to show in a different color. So the x values are not changing at all. They're going to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. However, the y values, they're going to be multiplied times 1/2, and then we're going to subtract 1. So 0 times 1/2 is still 0. 0 minus 1 is negative 1. 1 times 1/2 is going to be 1/2, and then 1/2 minus 1 is going to be negative 1/2. 0 times 1/2 is 0. Subtract 1, we get negative 1. Negative 1 times 1/2 is negative 1/2. Subtract 1, you get negative 3/2. And then again, 0 times 1/2, 0 minus 1, we get minus 1. Now let's go ahead and start plotting these points here. So we're going to plot the points in red. 0, negative 1. I might need to zoom in a little on this graph here. Pi over 2, negative 1/2. So there's pi over 2, negative 1/2 would be right there. Pi, negative 1. 3 pi over 2, negative 3/2. So negative 3/2 is negative 1.5. It should be right there. And then 2 pi, negative 1. Now we can see the pattern. I'm just going to continue the pattern real quick, just to get a nice clear picture for our graph. And now let's go ahead and graph this transformed sine function. So I'm going to do this in a little dash graph, or dash line rather. I'm doing this with a dash line because this is not technically the graph that we want our answer to be. Remember, we're trying to graph 1/2 cosecant of x, but we're going to graph 1/2 sine of x minus 1, and then use this graph and kind of flip it inside out. All right, so we've graphed y equals 1/2 sine of x minus 1. And when we go to graph cosecant of x, remember we talked about that the maximums for the sine function are going to be the minimums, for the cosecant function. Same thing for the minimums of the sine function. The minimum for a sine function is going to be the maximum for that chunk of the cosecant function. But we also need to plot our asymptotes. So any one of these points that are on the midline for this transformed sine function are going to be a location of a vertical asymptote. So let's put vertical asymptotes at all of those locations. Again, any point that's on the midline. So 0, pi is on the midline, 2 pi is on the midline, 3 pi is on the midline. Those will all turn into asymptotes. You need to have your asymptotes graphed for full credit. And then now, each of these maximum points are going to be flipped up. And the minimum point is going to be flipped down. Okay, and that is a great graph of our 1/2 cosecant of x minus 1. Again, we used 1/2 sine of x, since sine is the reciprocal, graphed its parent function, or really rather plotted the parent function in the table, transformed the points of the parent function based off of the transformations, plotted the points, and then used that to graph 1/2 cosecant of x minus 1. Okay, now let's do one more problem. Let's do problem number 3 from the third section. Since we did 1 from the first section, 2 from the second section, let's do problem 3 from the third section. But first, let's read our directions. For this section, simplify each complex number raised to a power and convert to rectangular form. Then, plot the result on both the polar plane and the rectangular plane. So, simplify each complex number, convert to rectangular form, plot on the polar plane, plot on the rectangular plane. So we get a few different things that we need to do here. So looking at number 3, we have 3 cosine of 150 degrees plus I sine of 150 degrees, all raised to the second power. So it looks like we're using de Moivre's theorem. Remember, de Moivre's theorem is a method for us to raise complex numbers to powers if they're in polar form. Now this is in polar form, and remember that de Moivre's theorem says whatever the modulus is, raise it to that power. So we'll have 3 to the second power. And whatever the argument is, in this case the argument is 150 degrees, multiply the argument by that power. So this would be cosine of 2 times 150 degrees plus I sine 2 times 150 degrees. Going through and simplifying, 3 to the second power is 9. 2 times 150 degrees is going to be 300 degrees. And this is our simplified version in polar form. Okay, so I'm going to go ahead and write polar form. Now the instructions also want us to convert to rectangular form, because we're going to want to plot both the polar form and the rectangular form answer. So let me grab a different color here. I'll grab green. Let's take this and let's convert it. So to convert from polar form to rectangular form, we're going to go ahead and calculate the cosine of 300. We're going to calculate the sine of 300, and we're going to multiply those by 9. So using our unit circle, the cosine of 300, let's look at our unit circle. Well, here's 300 degrees. Cosine's the x value, so we have 1/2. And then the sine of 300 is going to be negative square root of 3 over 2. So we're doing 9 times 1/2, positive 1/2, and negative square root of 3 over 2. And don't forget that this piece also has the I with it, right there. So let's go ahead and distribute our 9. This is going to give us 9/2 minus 9 square root of 3 over 2, I. Now, if we want to be technical about it, the I would actually go after the 9. That's just a notation thing, so this would be 9/2 minus 9I square root of 3 over 2. And this would be our rectangular form. I don't like that. I want the shaded in box. There we go. Better. Now, this is our rectangular form. I'm going to write rectangular. But remember that we're going to have to graph this. And I don't think many of us can look at this and say, oh yeah, I know exactly where 9 square root of 3 over 2 is. So let's go ahead and estimate these as decimals. If I estimate this as a decimal, this is going to be 4.5. Plugging the 9 square root of 3 over 2 into the calculator, we're going to get 7.8 approximately. So this is 4.5 minus 7.8i approximated. So let's go through and see if we've met all our conditions so far. We simplified the complex number. We converted it to rectangular form. Now we need to plot those results on the polar plane and the rectangular plane. And that's why we needed both the polar form and the rectangular form. So obviously we're going to use the polar form to plot on the polar plane here. So we have 9 as the modulus. We have 300 degrees as the argument. So what that's telling us to do is we're going to want to go to the 9th circle, which is right there. And we're going to put a point on the 9th circle at 300 degrees, which is right there. And because this is problem number 3, I'm just going to put it number 3 right there. Next, we want to plot the rectangular answer, the rectangular form answer, on the rectangular plane. And we're going to go ahead and assume that these are moving by ones. So this is going 1, 2, 3, so on and so forth. This is going I, 2i, 3i, 4i, so on like that. So we want to plot the point. Again, we're going to use our estimated point, 4.5 minus 7.8i. So I'm going to zoom in a little bit here, 4.5. 1, 2, 3, 4 and a half would be right there. And then we're going to go down 7.5, or about 7.8. So 1, 2, 3, 4 and a half. 1, 2, 3, 4, 5, 6, 7.8. About right there. Notice something that's actually really cool is that when you plot in polar form and then you go and plot in rectangular form, if you were to overlap the polar graph with the rectangular graph, those points would actually overlap as well if they were scaled the same. So pretty neat. But these have been 3 problems to help prepare us for the performance final. I'm going to be putting the key to all the problems up on eClass. Make sure you check it out. And this is Mr. Helk signing out.